Hey, this is Horner, and we're going to take a look at this first question, which is 2013, number 3. For rotational kinematics, it's got rotational inertia and rotational energy in it. First thing I would do on this problem is most likely you're going to need to draw a free body diagram at some point. So let's do that first. To draw that free body diagram, I'm going to go ahead and put a dot here. And then going straight down is going to be mg. And then I have two ropes. And for these two ropes, I'm going to put T, and then I've got an applied force over on the other side. So that's the situation that we're looking at. First thing they want us to do is calculate the magnitude of the force FA that will hold the disk at rest. So here we know that the sum of the forces is equal to 0. So this would be 2 times the applied force minus mg is equal to 0. And the reason I say it's 2 times the applied force is these two are going to be the same when it's at rest. So now at this point we can just say this is equal to FA is equal to mg divided by 2. And so now we're going to have FA is equal to 2 times 10 divided by 2, and that's just equal to 10 newtons. Points on this one, you would get 1 point for showing some of the forces is static, which is 0, and you get 1 point for doing the rest of the work. If you just put 10 newtons, you would not, so please realize you've got to put all this down in order to show them you know what you're doing, physics-wise. Next part of the question, this one I didn't give you really enough room to do it, so I'm going to show you how to try to get it to fit. I probably will go down below the line, but that's probably going to be about it. So here it says at time t the force is increased to 12 newtons, causing the disk to accelerate upward. The rope does not slip on the disk as it rotates, so they want us to calculate the linear. So be careful, they want the linear acceleration of the disk. We know the sum of the forces here should be equal to ma, which means that I have both Fa and T pulling up on the wheel, and then I have mg pulling down on the wheel, and that should be equal to mass times acceleration. So that, just writing that point, that part right there, should be 1 point. So we're going to put 1 point in there. Next part of the problem, they want you to show that torque is equal to I alpha. So this would be the force applied times the radius, so that would be torque, minus, that would be this force, but then we're thinking about it circular motion, so we've got to put the R there. And then we're going to subtract off TR here, and that should be equal to MR squared all over 2, and then that is multiplied by our good friend alpha. Okay, so we also know that alpha is equal to the acceleration over the radius, and so now I have FAR minus TR is equal to MR squared over 2, so that's our I, and then we're going to take that and multiply it times A over R, so that's our alpha. And now we can go through and cross off any of the R's. So RR, that one goes goodbye, and then this, so the only R left is this one. And now we have FA minus T is equal to, and now we've got MA, that's M lowercase a, not big A. So mass times acceleration all over 2. So that part is worth 1 point. So we've got 1 point here. We've got 1 point for these two. We've got 1 point for recognizing all of this. And now we're going to combine a couple of different equations. We're going to combine this equation and this one. And when we combine those two equations, you're going to get the following thing. We'll have 2 times FA minus mg is equal to 3/2 m times A. Now we're going to say A is equal to 2 over 3 times, and then we've got 2 FA, that's the applied force, over M, and then that quantity minus G. And then we can say A is equal to 2 over 3 times 2 times 12, and that is all over 2 minus 10. And so our final answer here is the acceleration is equal to 1.47 meters per second squared. And so then that is your last point. So in this one, notice I have 2 times FA, so really I've combined two of the equations here. I've combined this equation and this one. And that's why, so these two make this equation. And that's what I meant by combining the two equations. Next thing that we need to do is it says calculate the angular speed. So here we had the linear acceleration. Now they want us to find the angular speed of the disk at t is equal to 3 seconds. So we just found the acceleration, so let's go ahead and do this. So we have the angular speed is equal to the original angular speed plus alpha times t, and I know alpha is equal to a over r. So if you put that, you end up with 1 point. And then omega original is equal to 0. So our equation here is the angular speed is equal to alpha times time all over r. And so that's equal to 1.47 is what we found out in part B, times 3 all divided by 0.1. And when you get done, you should get 40. And then remember, it is a radian per second is our omega speed, or our angular velocity. Next thing they want us to do, one more thing we need to do here. This was, oops, let's change colors here. This was a point, and then you get 1 point here. So it's basically showing the initial condition and then showing the physics with the math that comes after that. Next part of the problem is to do a little bit of energy. So it says calculate the total increase in mechanical energy of the disk from 0 to 3 seconds. So first thing we need to do is say the change in energy is equal to the change of the potential energy due to gravity plus the kinetic energy. That's worth 1 point for just showing that. Our change in kinetic energy here is equal to 1/2 of the mass times the final velocity squared minus the original velocity squared plus, now this is linear, we also need the rotational, so this would be 1/2 I times omega squared. So that's the final rotational speed minus the original rotational speed. And we know that both the original rotational and the original linear are equal to 0. So that's really important because now we can remove some things. Next thing we need to do is find the change in the potential energy due to gravity, and that one is just mgh. So this is equal to mg times, now because this thing is falling, we can say that height is really 1/2 at squared. Remember, dy is equal to 1/2 gt squared or 1/2 at squared. So height can be that little guy right there. So that makes it really easy. Next part is to combine these two equations together. So we've got change in energy is equal to mg times 1/2 at squared plus 1/2 mv squared plus 1/2 I omega squared. And you get a point for that. You also get a point up here for showing this equation and then recognizing your original angular and original linear speed are both 0. Next part is to just do some rearranging, trying to put things in, make it so it all comes out right. So here delta E, or the change in energy, is equal to mg times 1/2 at squared plus, now we have 1/2 of the mass times, remember velocity would be r times omega, and that's squared, plus 1/2, and then I is mr squared over 2 for this object, times omega squared. And now we can go through and do some combining of some terms, so this would be 1/2 mg at squared plus 3/4 mRW squared. So that's just from combining everything we had above. Now let's plug some numbers in. So this is delta E is equal to 1/2 of 2 times 10. Oops, that's not 1/10. Should just be 10. 2 times 10 times 1.47 times 3 squared. So those are all our values. That 1.47, remember, came from part B. Plus 3/4 of the mass, which is 2, times 0.1 squared is our angular speed, times the radius, which is 44. And that one, I think, I dropped off a squared somewhere. So there should be a squared there. Okay, so now that we've got everything in, we should end up, when you do your math, with 144 joules. Next part says the disk is replaced by a hoop that has the same mass and radius. Indicate whether the linear acceleration of the hoop is greater than, less than, or the same as the acceleration of the disk. And here it's going to be less than, because the rotational inertia of the hoop is greater than that solid disk of the same mass and radius. Therefore, we can say the acceleration of the hoop is less. So remember, a hoop takes a lot longer to get it going than it does if you have the same size and the same radius, same mass disk. This one takes longer to get going. This one would win the race. And that is the end of this problem.